I want to do a little video here on something kind of specific, and that's tension. All right, and this is just a type of force that's present in a string or a rope, and there are a few little things that go along with this. A few different types of problems. One is just regular old like problems where you have an object hanging from something, or maybe even two objects hanging, and you have these two ropes that they're hanging from and the tension that's in those ropes. And the other is pulley problems, where you have some sort of pulley and you have maybe some other object here and then a rope stretched over the pulley, and the tension in the rope can help how these things interact. So like say that was on a table or something like that. So like these kind of problems is basically what we want to do here. And so we want to look at the tension in these ropes, and the rules that we'll talk about for this, which really just is the one rule, applies whether or not it's bending over a pulley like this or it's in a straight line. And basically tension is the force that's transmitted through a rope or a string or something like that. And the way it turns out is that the rope is going to be connected at both ends from one object to another. So if we're talking like, here's object A and here's object B, whatever they happen to be, whatever object A, object B happen to be. So like this could be like a zoom in of this spot here, or this being bent over that like that. So this would be object B, and we would have some rope connecting between them. And the tension in one single rope is the same at both ends. So what would happen is this rope would be pulling up on B, okay? It'd be pulling up on B, and that would be whatever this tension is, and then it would be pulling down on A in this example. And whatever that is, this tensions would then be the same. They're just that this is the tension acting on B, and here the tension is acting on A, and of course they're in opposite directions, almost like those force pairs for Newton's third law. But basically this can't apply this force here without that pulling down on it. And so in one rope, same tension at both ends, just pulling in opposite directions and on whatever it's attached to. If we went to like this example here, we would have a tension pulling up on this one here, T, and then another tension over here. Well, it'd be the same tension, T, just acting on a different object. So if this was block A and this was block B, then these two tensions would be the same. Over here, if you look at this one, maybe I'll draw that one a little bigger. If you have a tension, a block, another tension rope, and a block here, and let's say this is attached to an immovable ceiling or something like that. If this is object A or block A and block B, then you don't have just one tension here. You have this tension pulling up on A, whatever it happens to be, and we'll call it T1, and to be the same as what was pulling down on the ceiling, but the ceiling here, those dashed lines, it's immovable, so we can almost ignore it because we don't care what this is going to do. It can't be moved, so we're not worried about it. And then we'll have this tension down here between the two blocks. Again, it's at both ends of the rope, but it's not necessarily the same as T1. In fact, it isn't going to be the same as T1 in this situation, so this is T2 and T2. And so when you're doing force free body diagrams on this, you have to pay attention. When I do this on B, B would have gravity pulling down on it, and it would have this tension pulling up on it. So I'd have two forces on it, T2 minus mg. For A, on the other hand, I would have three. I'd have T1 pulling up on it, T2 pulling down on it, and then weight pulling down. I'd probably draw that weight in. So this would be mass of A times g. So it would have three forces. It'd be T1 minus mag minus T2. Right? So that'd be the net force on A. Net force on A, equals ma times A, and this would be T1 minus mag minus T2 equals ma. For B, on the other hand, it has just T2, and like I said before, it has its weight, which would be the mass of B times G, and so the net force on B, MBA, would be what would this would be T2 minus MBG equals whatever this is. If this was a static problem, if these weren't accelerating at all, they were just sitting there, then of course these accelerations would be 0 and it would just equal 0. But if this was on something like this, these were hanging inside an elevator that was accelerating upward or something, then this A would not be 0 and you'd have to worry about that at that point. But this would be your equations for them, your force equations counting tension. Then of course we don't care about the roof. What about this situation here? Whenever you have a pulley now, so let's talk about pulleys. So this is just hanging stuff. This would work dragging stuff, you know, if you had things like this hooked together and you were trying to pull with some force, then you'd have a tension in this rope, and then you'd have these same tensions here, and then a tension in this rope, and so you'd have T1, T2, T2, T3, T3 kind of thing, and you're trying to pull them like maybe along a table or something like that, and you could have those tensions. But what about these pulley systems? These you have to be a little bit careful about, okay? When you do one of these pulley systems, you're going to want to treat it like it's a straight line problem, almost like we want to just go ahead and just bend this out. So let me redraw that situation that we have there, and I'll show you what I mean by this. So let's say we have a block sitting here on the table, right? Here's our pulley, and then we have the other block hanging vertically, okay? We'll call this A, and this one can be B. And then we have this rope going over the pulley. That was not a very good rope. Let's put this rope right over the pulley there, attaches to this. How would we go about solving this? Well, let's draw in the forces acting on everything. So the forces on A, we have just this one tension in the rope, T, and then that same tension would be over here on A. It just because this is what we call a massless pulley, then this tension just goes over it. The pulley has no effect on it, no torque or anything like that. Then on B, we have the mass of B times G, its weight, and then that's it for B. On A, we have no other horizontal forces. We're assuming this is frictionless, so no friction, in which case we have nothing else horizontally. Now we could add a friction in if we wanted, but I haven't, it wouldn't be that big a difference. You just add the friction force back here the way we do friction, and it would just be another extra force on A horizontally. But then vertically speaking, what do we have? We have our normal force, or F sub n, whichever it happens to be, and then you have its weight pulling down on it. Now, since this is horizontal, this weight and normal force, they have no effect on the horizontal force of these tensions. And ultimately, if you did the vertical equation here, you would just get that MAG equals this normal force, because this is perfectly horizontal, so it would have no effect. So we can basically ignore those for this problem, and we only want to talk about how does this accelerate, so how does A accelerate to the right and B accelerate down? Well, every inch that B moves down, A is going to move an inch to the right. So essentially the downward motion for B is equivalent to a sideways motion for A. So in order to take care of that and to account for this, what you want to do is you want to make a positive direction that bends over the pulley. So I would call this the positive direction, okay? So for over here, my positive direction is this way, and for over here, my positive direction is down. I didn't have to have done that. I could have pointed in the other way, in which case up would be positive here, and left would be positive here. It really doesn't matter. It'll just give you a different sign for your acceleration if you flipped it. It's just the choice of your coordinate system. But we basically want to bend our coordinate system over this. And the reason then for that is, again, because if B moves down, this moves to the right. And we want those to be the same so that we have the same acceleration, because if this accelerates downward, this is going to have the same acceleration just to the right. And so it's like this pulley system kind of just bends all our forces over. We're essentially taking this and turning the problem on its side. We're saying here's A, here's our rope, here's B, and we're trying to do it this way, where we're pretending we have A, here's T, and then gravity m2g. It's just some force over here. And we're basically going to solve it as though it is this situation, okay, where this to the right is positive. This is the positive direction. We're going to just basically pretend, so we're pretending that this is the situation we have. And the same thing if this is bent like up and over, like if it was, you know, a box and then it was over a pulley and then there was another box, and sorry, this is a quick little sketch, that should be, you know, straight over, but if we had 3 of these like this, we would basically do something like that and say like that's the positive direction, which would make up the positive direction over here, down the positive direction over here, and to the right the positive direction for the middle block. So just keep in mind you kind of do that. Even if we have one of these like this was inclined, then up the incline would be positive and down would be positive for there. So you just have to be very careful. You're trying to take these bent coordinate systems and turn it into something straight. So you almost want to pretend that you have this situation here where the gravity mg there is pulling this to the right. Okay, this and this are the same. So that's what you basically want to pretend when you're doing these and you write up your force equation. So if we were going to do that over here for this one, okay, we would, we would do the net force on A is equal to, and we're only worrying about horizontal because these just end up equaling each other and have no effect horizontal, just remember that. The only force on this, this is MA, and we want these to have the same acceleration, so I don't put a little subscript A on it. The only force acting on it is T. It's in the positive direction because to the right is positive up here, right? This little part up here, this is the positive direction, equals M sub A. Now, if there was a friction force pointed out this way, if that friction was there, then it'd be T minus F, because F always opposes the direction of attempted motion, or at least either motion or attempted motion. And then B, I would do net force on B. In this case, here, M2G is in the direction that I defined as positive. So for B, same acceleration, same A, it's M2G minus T. This T is now the negative direction because on this side up is negative, and this is MBA. So if there's no friction, then this will definitely be moving and it will be accelerating because there'll be nothing to stop it because we were pretending that wasn't there. So we don't have the minus F over here, which means this only has one force acting on it, which means it has to be an imbalance force, which means there has to be an acceleration, assuming this tension isn't 0, and this tension will not be 0 unless the mass of B is 0. In which case it becomes trivial. So at this point we can just, you know, start sub this over for T, go through and solve it the way you would normally. Okay? Hopefully that's a good introduction for using tensions and rope in the situations you can get into with a pulley, and doing that. And then of course the ones up above where you just have the rope attached between objects like that. Okay? That's about all that there is.